Assalamualaikum. Today we'll be discussing article number 27.3, a model for electrical conduction. Well, this article is somewhat similar to what we have done previously. We will consider a conductor, then the free electrons, and then apply potential difference across it. Because of the potential difference, an electric field will be generated, and it will be, experienced by the electrons, and the electrons then behave accordingly. So, in this article, as the article name suggests, that it's a model for electrical conduction, and this model was presented by Paul Drude in 1900. It leads to the Ohm's law and shows that resistivity can be related to motion of electrons in metal. So we will be uh, after derivation we'll be seeing that we have the equation for Ohm's law, that is J is equal to sigma E, and from there we'll see that we can find resistivity or its reciprocal conductivity. So after considering this, um, we'll see also, well, not in this course, but this model has certain limitation, and these limitations are that this model fails to explain the disparity between expected heat capacity or capacities of metals compared to insulators. And secondly, it fails to explain positive charge carrier as shown by positive Hall effect of certain materials. Otherwise, whatever we will try to find out using this model related to Ohm's law and conductivity or resistivity will give us the accurate values. But these 2 points, at these 2 points, this model fails to give us the accurate result. Now, to proceed with the model, we will consider a conductor which have a regular array of atoms plus a collection of free electrons called the conduction electrons. So, obviously in a conductor we have free electrons, and because of these free electrons we get current when we apply potential difference across it. So sometimes most of the scientists, they refer to these free electrons as conduction electrons, and in some other cases these free electrons or conduction electrons are also known as electron gas within the conductor. So when there is no electric field applied to the conductor, we have discussed earlier in article 27.1 and 2 that when the electrons, they are moving randomly within the conductor, they are moving with immense speed, and that speed is of the order of 10 raised to the power 6 meters per second. So and this is because of their thermal agitation, and the electrons, they are moving so randomly within the electron with this amount of speed. So these again, the point is that these conduction electrons in the metal are also known as electron gas. So there are three names now for these electrons in the conductor: free electrons, conduction electrons, as well as you may find another name, that is the electron gas for these electrons. As electrons are moving randomly in the absence of electric field, therefore there is no current, as the drift velocity is zero. So these are the points which we have already discussed in the previous article. So I'm going through these points quickly. So when we have not applied any electric field, then obviously there will be no current because the drift velocity is zero. So now what we'll do, we'll apply electric field to the conductor, and those electrons which are moving randomly within the conductor, they all start to move in a direction, and now they will have a certain value of drift velocity, as they will start drifting slowly in the direction opposite to that of the applied field, electric field, with average drift velocity, which will be given as Vd. This drift velocity, the value for this drift velocity is very less, that is 10 to the power minus 4 meters per second. Again, we have discussed it in the previous article. So the value for this drift velocity is so small, that is, we may say that the electrons, they are moving with the speed of a turtle or a snail. They are moving very slowly within the conductor after applying electric field. So now, this figure, this gives us an idea that before the application of electric field, electron was here and it was randomly moving within the conductor. So when we applied electric field, it starts to align itself in the direction opposite to the applied electric field. So now if electron is moving in this direction, it means that the direction of electric field is this. So obviously it's not like that if we have applied electric field immediately, all the electrons, and they will start moving straight. So obviously they will take a little time, and they will align themselves and then start moving in the direction opposite to that of the electric field. So this is after the field is applied, and this figure shows before the application of electric field to the conductor. So now, considering motion of free electron is independent before and after the collision. So what we will assume two things. Number one is that the motion of the free electron is independent before and after the collision. That the motion has nothing to the electron's motion has nothing to do when it's moving before the collision, and is not related to their movement after the collision. So these are two totally different entities. And second assumption is that excess of energy acquired by the electron, whatever the energy is acquired by the electron by colliding with one another or with the walls of the conductor, whatever the excess energy they have acquired in the electric field is lost to the atoms of the conductor when electrons and atoms collide. So this field can be attained because of colliding with one another or with the walls, and when it will happen when the electric field is applied. So they will lose all the energy to the atoms, and they will transfer this energy to the atom whenever they'll collide with them. So these are the two assumptions which we will make. The energy given to the atom will increase their vibrational energy, causing the temperature of the conductor to rise. So this is a very general thing to note, that whenever the atoms, they gain energy, what will happen to them? Their vibrational energy increase, and when the vibrational energy of the atom it increases, the temperature of the conductor will rise automatically. So now we will derive an expression for Vd using the Drude's model. So let us consider Me be the mass of electron which have charge Q, which is equals to minus E, which is subjected to the electric field E. The electrons will experience force, and this force is given by the equation F is equal to QE. As this force causes electrons to accelerate, we may also write F is equal to ma. because when we have applied this electric field to the electrons, the electrons, they will start moving in the direction opposite to the electric field. If the electric field is in this direction, then the electrons will move in the opposite direction. So because they are accelerating, the force which we will consider is F is equal to ma. That is from the Newton's second law. Now comparing equation 1 and equation 2, we'll get QE equals to MEA. From here I can find the value of acceleration, that is A, and I know that acceleration is a vector quantity which is equals to QE over ME. So this is my equation number 3 now. A is the acceleration which occurs between the collisions, resulting in attaining drift velocity by the electrons. If Vi is the initial velocity. Let us suppose that Vi is the initial velocity at some time taken to be t equals to 0, and velocity after collision be Vf at some time t. So if we have these parameters, the first thing which comes to our mind is equation of kinematics. If you remember, we have three equations of kinematics, that is Vf is equal to Vi plus At, 2s is equal to Vf square minus Vi square, and s is equal to Vit plus half At square. So here we will use first equation of kinematics, that is Vf is equal to Vi plus At. We have the value of A. So from equation number 3, I replace this A with equation number 3, and we'll get Vf is equal to Vi plus QE over ME into T. As at t equals to 0, we'll assume that our initial velocity is also 0. So Vf is equal to QE over MET. Now what we will consider is that where these are, this is what we get from acceleration, and this is the time, the final time corresponding to our final velocity. Now if I consider this Q, it's a constant, and me is a constant value. So if I increase the value of electric field, the final velocity, or which we will later see that is basically drift velocity, the value for drift velocity will increase, and this time will be the relaxation time between the collision. If the relaxation time or the time between two collision it increases, we will see that the drift velocity, it will also increase. So the drift velocity will depend directly upon electric field as well as the time between the collision. So now we'll see that this t is replaced by tau, that is the average time interval between successive collision. So we'll replace this t with tau, and when I replace this t with tau, and this velocity will become the drift velocity, and we have this equation number 5 for our drift velocity. As already discussed in the previous article, we have calculated the current density to be equal to J equals to NQVD. From equation 5, I can replace VD over here. So NQ, QE over ME into tau. This can be written as NQ square E over ME into tau. So where N is the number of charge carriers per unit volume. We also know that Ohm's law is J is equals to sigma E, So I can compare this A with equation number 6, and will get the value of conductivity, that is sigma E is equals to NQ square E over ME tau, cancelling these E's from both sides, and finally I get this sigma equals to NQ square over ME into tau. Or if I want to calculate resistivity, the resistivity is equals to ME over NQ square tau. So 7 and 8 tells us that sigma and the resistivity does not depend upon E or its strength. What it depends upon is the relaxation time, or time between two successive collision uh, for conductivity. If the time is greater, that the time between two successive collision is greater, then obviously the value for conductivity will be greater. But in case of resistivity, it's simply the reciprocal. So if it is greater, then its value is smaller, the value for resistivity, and if it is smaller, the relaxation time, then the resistivity value for resistivity will be greater. So this is what we have concluded by using Drude's model, that the resistivity that we have said that by using Drude model, we'll see that it leads to the Ohm's law, and it shows that the resistivity can be related to the motion of electrons in the metal. So this motion is represented by tau in the equation. So if they are moving in such a way that they are colliding with one another after a longer period of time, then their conductivity will be higher and their resistivity will be smaller. So this is what we have proved in this article. Okay, now moving on to article 27.4. uh, this article is a very simple one, and it's about resistance and temperature. If you remember that in mechanics we have done linear expansion or volume expansion. Uh, this formula which we will be using in this article, it is the same that we have used in case of linear expansions. Simply in mechanics, when we are talking about linear expansion, we use L naught, and alpha stays the same, that is coefficient of thermal expansion, and T and T naught stays the same. So only we have replaced these L's with resistivity, and for other we'll see that this resistivity is replaced by R, that is the resistance. So this is the same formula which we use in mechanics for thermal expansion. So we'll start the article that over a limited temperature range, the resistivity of a conductor varies approximately linearly with temperature. So resistivity varies linearly with temperature. If the temperature rises, the resistivity will rise. So because with increased temperature, the electrons, they are moving more randomly, and when they are moving more randomly, they are colliding more oftenly with one another, and in doing so, the collision, this time between two successive collision decreases, and when tau decreases, then resistivity will increase. So this says that it varies approximately linearly with temperature, and yes, this it clicks our mind that this can happen. So rho is equal to rho naught into 1 plus alpha T minus T naught, where alpha is the coefficient of resistivity over here, which in mechanics was used to be coefficient of thermal expansion, and from 1 we can find the value for equation to find the value for alpha. That is rho is equal to rho naught plus rho naught into alpha delta t. I have done nothing. I have simply multiplied this rho naught within the parameters inside the bracket, and then I'll simplify it. That is rho minus rho naught will give me delta rho, which is equal to rho naught alpha delta t, dividing this rho naught and delta t to the left hand side, and I'll get alpha is equal to delta rho equals to rho naught over delta t. So this is these if I write down the units, the unit for delta rho and rho naught will cancel, and I'll get per degree Celsius. So the unit for alpha is per degree Celsius. Again, alpha varies from material to material. Every material has its own coefficient of resistivity. So whatever material we'll choose according to our problem, uh, it will, the value of alpha will affect it. So we have to be careful in selecting our problems. Okay, now what I can do is I can write this equation for r, or if I simply want to write equation number 1 for r, what I'll do is I'll simply uh, write r equals to r naught into 1 plus alpha into t minus t naught. So this is the equation for resistance, and this equation came from a rho, because we know that rho is equals to r a over l. So if I replace rho on both sides, so for here I have r a over l, and on the right hand side I have r naught a over l. A over l will cancel from both sides, and finally I'll get this equation over here, and this is how I can find the resistance effect on temperature, how temperature affects the resistance. So this in the next slides or videos we will solve some related example problems, so it will become more clear to you.